Good. Let's move on to problem 4. First, let's read the problem. The long sides of a rectangle are divided into 4 equal parts and the short side into 3 equal parts. One point on the other side is joined to all the others. What fraction of the area of the large rectangle is the area of the shaded rectangle? Whoa, now we're not given any side lengths. So what do we do to continue this problem? And the trick here is to use the power of algebra. They told you that this side is divided into 4 equal side lengths. So let's call each part a unit. They also told you that this is divided into 3 equal parts. So let's call each of those parts B units. Great, because now we have the power to do the area of the large rectangle. So area of large rectangle will be base times height. So using the base of 4a, the height will be 3b, and this evaluates to 12ab. Good, so we made some progress. Now we need to continue further. Now, looking at the shaded region consists out of, it's not a known shape, but it can be broken up into 6 triangles, okay? So it can be broken up into 6 triangles. So let's label the triangles 1, 2, 3, 4, 5, 6. Good. Now let's look at triangle 1. If I'm using the base A, I'm going to need its vertical height h. And we don't know what it is. So time for more variables to pop up. Now this point P is on the one side, but we don't know if it's the midpoint. Let's read the problem carefully. One point on the other side is joined to the others. We don't know if P is the midpoint. So now what we have to do is, let's call the distance from there to there x, and we need another variable. Let's call the distance from there to there y. So if you got stuck, here is now a good point to pause the video and see if you can complete it and get the same answer as I do. So using the power of algebra and more variables, we ended up having to use the variables a, b, x, y as indicated in this diagram. Good. So now let's calculate the area of the shaded region. So area of shaded region will be the area of triangle 1 plus 2 plus 3 plus 4 plus 5 plus 6. Good. Now, can we do the area of triangle 1? Yes, we can, because we have a base and a vertical height. So the area of 1, do you agree? It's a half a times x. 2, if I'm using the base of a, then its vertical height will be x. So 2 is an obtuse triangle. We had this discussion earlier in the video. So the area of 2 would be a half a times x. 3, goodness, I was mixing up. So triangle 2 is over here. So triangle 2, if I'm using a base of a, the vertical height will be y. Good. 3 is now the obtuse case. If I'm using a base of a, then the vertical height will be x. So that will be a half a times x. 4 is what's sitting over here. So here it's again an obtuse triangle. So a base of a and a vertical height of y. So it's a half a times y. 5, we select the base of b. And if we select the base of b, this will be the vertical height, which is the one side length of the rectangle, which is 4a. So what we have is the following. Is the area of triangle 5 will be a half b times 4a. And triangle 6, if I'm using the base of b, then the height will be 4a. Right, and now let's continue the maths. So I have a half ax over here and another half ax over there. So that can be simplified to just being ax. Here I have a half ay plus a half ay. That can be simplified to ay. A half times b times 4 times a is the same as a half times 4, which is 2. And b times a is the same as a times b. A half times b times 4 times a half times 4 becomes 2. And b times a is the same as a times b. And so we get the following popping up. So we have ax plus ay plus 2ab plus 2ab. We can simplify to 4ab. Goodness, all right. So we got somewhere, but now we're still a little stuck. Well, we know here we can take out a common factor of a, and we're left with a times x plus y plus 4ab. You will see I didn't take out the common factor a here for a specific reason. Good. Now, we still have 4 variables lurking here, a, b, x, and y. Can we do something special? Remember, we are dealing with a rectangle. And if you're dealing with a rectangle, we know that opposite sides are equal. So we see the top is 4a and the bottom is 4a. 4a is equal to 4a. It's not really helping. I hope you see where I'm going. On the left, we see x plus y. And on the right, we see 3b. So we see that x plus y must equal to 3b. This is a crucial observation that allows us to use it over here, because now replacing that x plus y with 3b, we now have the following popping up. That a times 3b plus 4 times ab becomes 7ab. And now we're ready to answer what the fraction is. The fraction that we're looking for will be shaded divided by the large rectangle, and the shaded part was 7ab, and the area of the rectangle was 12ab, and now some magic happens. The a's cancels, the b cancels, and the answer is 7 over 12. Pat yourself on the back if you also got 7 over 12. Very important, this answer is independent of what a, b, x, and y is. So no matter what values a, b, x, and y you choose in all those diagrams, if you calculate the shaded area divided by the area of the large rectangle and all of those possibilities, it will be 7 over 12. And this is another important problem, because even though the problem started without algebra, we needed algebra to eventually help us out here to show why the ratio of the two areas is 7 over 12. Good. I hope you enjoyed that problem. Let's do another problem. Problem 5 goes as follows. The large quadrilateral shown has 2 right angles, and 2 of the sides have lengths 7 and 10 centimeters. Points B and D are on the remaining 2 sides, so that AB is 2 centimeters and DC is 6 centimeters. This is not drawn to scale, but you can see the information makes sense. Our job is to calculate the area of the shaded quadrilateral. So it's a quadrilateral, so it's a polygon with 4 sides, but it is not a square, so we cannot use the square formula. It is not a rectangle, so we cannot use the rectangle formula. So we now have to be creative in finding the area of the quadrilateral. Now, you saw in the previous problem that playing with triangles is much more fun than playing with odd shapes. So can we turn quadrilateral ABCD into parts that consist only out of triangles? Can we triangulate it? Yes, we can. So the key step, the genius step to solving this problem is join A to C. So now let's join A to C in a straight line. And so the area of ABCD is the area of ABC plus the area of ADC. So every quadrilateral you can break up into two triangles by joining two opposite vertices. All right, is this useful or helpful? You've got to ask yourself that question. Now let's have a look at triangle ABC. Now, do we know AC? No. Do we know BC? No. But we know AB. They gave us, that's 2. Good. Now, if I'm going to use the area of a triangle is a half base times height, I need to know its associated height. And what do you know? It's given as 10. So ABC is an obtuse triangle. So its vertical height is outside, and we are so lucky that it's given as 10. So this area of triangle ABC is therefore a half, 2 times 10. Plus, now let's have a look at triangle ADC. Are we given AD? No. Are we given AC? No. Are we given DC? Yes, it's 6. So using this as a base, we need its associated height, and its associated height is again outside, it is 7. So we can calculate the area of triangle ADC safely. So it's a half of 6 times 7. And now let's do the maths. A half times 2 times 10 is 1 times 10, which is 10. A half times 6, which is 3. So a half times 6 times 7 is 3 times 7, which is 21. 10 plus 21, do you agree? It's 31. And in this problem, we're given units, so it will be centimeters squared. And that is the answer to problem 5. So problem 5 was a nice quick one, is to say it's not a rectangle, it's not a square, so I have to come up with a clever plan. And the clever plan was to join A to C, and now you have to compute the areas of triangle ABC and ADC, where we get to use our formula of a half base times height. And we got it quite easily. A nice little problem. You can show your friends at school. Good. Let's move on to problem 6. Now problem 6 is about circles. And here we go. AB is the diameter of the circle, and AB is 10. If the area of triangle ABC is 11, find the perimeter of triangle ABC. Now, before we do any mathematics, one thing that you got to know is that something very special happens. If you take half a circle, let's take half a circle, and if you take half a circle, that let's call the center of the circle O, and let's call the diameter AB, as we have in this case. And now if I construct any point on a semicircle, let's call that point C, and let's connect A to C and B to C. Let's see if we can calculate angle C. So let's find angle C. All right. Now remember, O is the center of the circle, or the center of the semicircle. So what does that mean? That means the following: that if I connect A to O and O to C and O to B, they all have the same length. This is very important. That is what it means for O to be the center of the circle or the semicircle. And that means that AOC and OBC are what kind of triangles? Yes, they are isosceles triangles. And what do we know about isosceles triangles? We know in isosceles triangles that angles are equal. So if this is alpha, then this has got to be alpha, because the corresponding sides are equal. If we call this angle beta, then this angle is beta because the corresponding sides are equal. So that's very important. A triangle AOC and triangle COB are isosceles triangles. So those two angles must be the same. Let's call it alpha. Those two angles are the same. Let's call it beta. Great. Now let's continue with some more algebra. We know that the sum of the angles in a triangle add up to what value? 180. So we know that angle A plus angle B plus angle C must add up to 180 degrees. Now in this diagram, angle A, we're using the Greek letter as alpha. Angle B is beta. And now angle C is this big angle over here, marked, I hope you can see it. So that will be alpha plus beta is equal to 180 degrees. Great. And now let's continue the maths. So we get that alpha plus beta is 180 degrees. Can we simplify it? Yes, we can rearrange this and we can get, how many alphas do we have on the left? 2 alphas. How many betas on the left? 2 beta is equal to 180 degrees. And we can divide by 2. So we see that alpha plus beta is equal to 90 degrees. And now let's think about it. But isn't angle C equal to alpha plus beta? So alpha plus beta is equal to 90 degrees. And here we have a little theorem that if you form an angle in this manner in a semicircle, that angle C is always 90 degrees. And this is very important to us because that means that triangle ACB is a right angled triangle. And because it's a right angled triangle, we get to use which theorem? Yes, the theorem of Pythagoras. Alright, but now we're not done yet because now we need to do some more maths. Good. So our job is to find the perimeter of triangle ABC. But what information do we know? We know that the area is 11. We know that AB is 10. And we know that by this theorem, that angle C is 90 degrees. So we can also use the theorem of Pythagoras. So just like this proof, where I used algebra to show why angle C is always 90 degrees, we are going to use variables again. So I'm going to use the convention. If this vertex is capital A, then the distance from B to C is little a. If this vertex is capital B, then the distance from A to C is little b. Right, so now let's write down what we know. Using Pythagoras, I know that a squared plus b squared is equal to the hypotenuse, which is 10 squared, which is the diameter. So I know that a squared plus b squared is equal to 100. Good. We also are told that the area of the triangle is 11. So using the area, I know that because it's a right angle triangle, that the area of the triangle will be a half AB, and that's equal to 11. So if we double this up, we get that AB is equal to 22. Good. All right. And what are we interested? We're interested in the perimeter. So the perimeter in this case will be AB plus BC plus CA. So AB, it's given as 10. BC, we're calling it the variable little a, and CA is B. So we're interested in 10 plus A plus B. But we don't know A, we don't know B. But what you do know is that a squared plus b squared is 100 and AB is equal to 22. So let's put on our thinking caps and let's think. We don't really want to know what A is. We don't really want to know what B is. We want to know what is A plus B. So typically in Olympiad problems, you do some reverse engineering. So we're interested in the perimeter. So we're interested in knowing A plus B, because if we know what A plus B is, we can calculate 10 plus A plus B. Good. So we're interested in knowing what A plus B is. Well, using the theorem of Pythagoras, we now know that A squared plus B squared is 100, and we know that AB is equal to 22. Is this useful? It's got to be useful, because with an Olympiad problem, you always get enough data to help you to solve the problem. Now, for fun, let's calculate A plus B squared. Now, just like the theorem of Pythagoras, we know that A plus B squared is equal to A squared plus twice AB plus B squared. Now, this we can rewrite as a squared plus b squared plus twice ab. And now we're in business because we know that a squared plus b squared, that is given as 100. And twice ab is 22. So this becomes 100 plus 2 times 22, which is 144. So now we know that a plus b squared is equal to 144. So thus, a plus b is equal to the square root of 144. And I hope you can do it without a calculator. The square root of 144, that works out to be 12. And so working out what a plus b squared is, and finding that it's 144, we managed to find out what a plus b is. Without knowing what a or b could be, we know that a plus b is 12. And now we're happy because now we know that 10 plus a plus b is 10 plus whatever a plus b is. And we just discovered that a plus b is 12. So 10 plus 12 becomes 22 units. And that is the answer to this problem. Good. I hope you agree with this calculation and maybe rewrite this in a shorter way, in a more elegant way, to see that the answer to this problem is indeed 22. Good. So enough information was given for you to work out that the perimeter of triangle ABC is 22 without knowing what the distance from B to C is, or the distance from A to C. Great. Okay. Let's have a look at another problem. Okay, let's first read the problem. In the figure alongside, the area of each of the small circles is 2019 square centimeters. They are arranged in the form of a cross inside a circle whose radius is 3 times as large as that of each small circle. What is the area of the shaded region? So again, we're going to use the power of algebra to help us to solve this problem. Now, given a circle, the most important point is its center. Just like the previous proof, a lot of the time, if you're not given the center of a circle, draw the center of the circle. So what you have is you have your little cross over here. All right. And now say each radius is r. So that's r, 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 and that's r. Great. Okay. So some must know that the area is pi radius squared. So a circle with radius r has an area of pi radius squared. And if you're interested in the circumference, that is twice pi radius. So this is some must know information about circles that you should know for school and for Olympiad problems. That you want to know the radius. Knowing the radius of a circle, you can compute the area quickly. It's pi radius squared, and you can calculate the circumference. So typically when you have circles, you don't talk about its perimeter, you talk about its circumference. The circumference will be 2 pi radius. Now pi is a very special constant, which you will see at university also quite often. Pi is a special number that is more than 3 and less than 4. So pi is approximately 3,14, etc. Some people spend their time trying to memorize the digits of pi. Pi is known as an irrational number. Irrational meaning that it cannot be written as an integer divided by an integer. So pi has very special properties. It's a very important mathematical constant. 3,1415, etc. And it's known as an irrational number, meaning that it cannot be written as a quotient of two integers. And there are so many fun problems about pi that you can explore and play with. Alrighty, so where are we going with this problem? Alright, we don't know the radius of this, but they tell us that each of the 5 small circles has a radius of 2019 squared. So in essence, if each of the circles have radius r, we now know that pi radius squared is equal to 2019. Okay, now let's go back to the problem. They want to know the area of the shaded region. So let's call that part x, and let's call that part x. So by symmetry, we know that this part over here will also be x, and this white part over here will also be x. And just like the previous problems we tackled earlier, let's do some area counting. So we know that if those funny shaped areas, so x plus x plus x plus x, so we have 4 of those, plus the 5 circles. If we add up those areas, it will be the area of the big circle. Do you see it? Let's call this part has area x. So this part also has x. This funny part over here has x, and this funny part over here has x. So now if I go adding up the 4 funny parts plus the 5 circles, I'll get the area of the big circle. Okay, so what does that mean? X plus x plus x, that is 4x, plus the 5 circles. Each of the 5 circles have the same radius, and which is r, and so its area will be 5r squared pi. That's the area of the big circle, which is pi times whatever the radius of the big circle squared is. And now look at the diagram. What is the radius of the big circle? It's obviously the distance from O to over there. Let's call it P. So the distance from O to P. So it's there to there to there to there. And in terms of R, what is it? Yes, it's 3R. Now let's try to put everything together and see what we get. We get that 4x plus 5r squared pi is equal to 3r squared, means 3r times 3r, which is 9 pi r squared. Now I've written this in a funny manner, but you can clearly see that 4x will be 9 pi r squared minus this 5 pi r squared. So 9 pi r squared minus 5 pi r squared becomes 4 pi r squared. And so we see that x becomes the following, dividing by 4, x becomes pi radius squared. And we're given that pi radius squared is the area of one of the small circles, which is 2090. So what have we established? We have established that the funny part x is the area of one of the small circles, which is given as 2090. And so now we can answer the problem and say the shaded, so area of shaded region is equal to 2 times x, which is 2 times 2019. And now we got to double 2019. So double 20 is 40, double 19 is 38. So the answer is 4038, and we're given units, so centimeters squared. Boom, bang, we are done. We have solved this problem. And there you go. The area of the shaded region is 4038 square centimeters. And we are done. Just to recap, again, we use algebra to help us out here to solve this problem. And you can see that you needed to know that the area of a circle is pi radius squared. And a circle is a very useful shape. It's not a polygon. So unlike a polygon that has many vertices, a circle is a shape with no vertices. And it's quite fascinating to see that each of those parts labeled as X has the same area as one of those small circles. Great! Are you ready for the last problem of the video? Here we go. It goes as follows. In the figure, the shaded area is 2/3 of the area of the smallest circle. It is also 3/8 of the area of the largest circle. If the radius of the smallest circle is 15 centimeters, what is the radius of the largest circle in centimeters? Okay, so there are many ways of solving this problem. Okay, so I'm going to use the following notation. Let R footscript S equal to 15 centimeters. So area of small circle is pi its radius, which is RS squared. So that will be pi times 15 squared. Great. And now they tell us the shaded area is 2/3 of the area of the smallest circle. So shaded will therefore be 2/3 times the area of small circle. So that will be 2/3 times pi times 15 squared. I'm not going to simplify that for now. All right. Let R be the radius of the big circle. So that means that the area of big circle is pi radius squared. And so again, knowing that the shaded area is 3/8 of the largest circle, then we can say that the shaded is 3/8 of area of large circle. What we have is then 3/8 times pi radius squared. Good. So what we have done in essence, using the given data, we have calculated that the shaded is given by this expression or it's given by this expression. And the area of the shaded region must be unique. That means that these two quantities must be equal. So therefore, we have that 2/3 pi times 15 squared must equal to 3/8 times pi times radius squared. And now let's see, can we solve for R? Well, we see the pi on the left and the pi on the right cancels. And what remains is the following. We have 2 times 3 times 15 squared is equal to 3/8 times R squared. And what we now can do is we can multiply both sides by 8/3. So if I multiply both sides with 8/3, I have 2/3 times 8/3 times 15 squared. That's equal to 3/8 times 8/3 times R squared. Maybe you are doing the algebra a little bit differently to what I am, but I want to demonstrate why multiplying both sides with 8/3 works, because that 8 at the top and that 8 at the bottom cancels, that 3 at the top and that 3 at the bottom cancels, 3/8 times 8/3 becomes 1. So on the right hand side we have R squared. On this side we have the following. We have 2 times 8, which is 16, times 15 squared. 3 times 3 can be written as 3 squared. This equation, I hope you agree with me, can be rewritten as R squared is equal to 16 times 15 squared over 3 squared, which is the following. 16 can be written as 4 squared times 15 squared can be written as 3 squared times 5 squared. Here I'm using the fact that a squared times b squared is equal to ab squared. This is another must know, over 3 squared. So now you can see that 3 squared and that 3 squared cancels. And what you're left with is 4 squared times 5 squared. Yes, you can work out 4 squared. Yes, you can work out 5 squared. But 4 squared times 5 squared can be written as 4 times 5 squared, which is 20 squared. So what we have is that r squared is equal to 20 squared. So r is equal to the square root of 20 squared, which is 20. And in this problem, we are given units, so we can give units in our final answer. So r is equal to 20 centimeters. And that is the answer to this problem. So again, using the power of algebra, we managed to turn the information into equations. And in this case, calculating the shaded area using the information twice, we got an equation, and that equation allowed us to solve r, which is the radius of the largest circle. And that is the reason why this quantity that we're looking for, we decided to call the quantity that we're looking for r. This is the end of the first video. Trust you've learned something, and join me next time for another lesson on areas. Have a nice day. Bye.